In Module 4 of Chapter 13, we're now going to look at the market maker profit and loss using the mathematics underlying the Black-Scholes option pricing model. One of the conclusions of the analysis done by Black and Scholes is that the price of an option must satisfy a partial differential equation. Namely, that, and you can see that on the right-hand side, this is the risk-free rate times the value, the price of the option. And notice on the left, this is a differential equation in C because recall, theta is the derivative of C with respect to time. Delta is the derivative of C with respect to S. And gamma is the second derivative of C with respect to S. So this is a differential equation in the price function C of S. Namely, this equation says that at every point in time, if you calculated these three derivatives of the price function C and inserted all these other R and S and sigma, you would have to get R times the price C. There are assumptions, of course, underlying the Black-Scholes analysis, and that is that we don't have dividends, and certainly this equation can be adjusted if the underlying asset pays dividends. That's not a problem, but in the form that we just saw, there's no dividends. The interest rate and volatility are constant. This equation explicitly assumes R and sigma are constant, and that the stock moves one standard deviation over infinitesimal time periods. We'll see this more in the context of Ito processes and Ito's lemma. But the intuition is that the movements of the stock in continuous time are the limits of the movements in a binomial tree when h goes to 0. And in a binomial tree, one can think of each step in the tree, the stock price is moving by plus or minus one standard deviation. And this equation is valid for European options, needs to be adjusted and reinterpreted for American, so we'll understand this as an equation for European derivatives. So this model for S is the continuous version of the binomial model. We're going to keep returning to this theme. We saw it in an earlier chapter that the the binomial distribution provides stock prices at expiry that are binomially distributed but approximately log-normally distributed. And in the binomial lattice, we have this defining property that, again, ignoring delta, little delta, the dividend rate, that the log ratio of prices has a drift term and a volatility term. And we'll see in a later chapter that, in fact, in the limit, when h goes to 0, the binomial model produces a log-normal distribution of stock prices. In particular, if we looked at stock prices at time capital T, and we look at the log of the ratio between stock prices at that time, which are randomly distributed, a random variable, divided by the initial stock price, they would be normally distributed. And the mean of the distribution would be the risk-free rate minus half of variance, and it's linear in time. And the variance would be sigma squared times time. And again, this is a property we've seen time and time again, where the mean of the distribution is proportional to time, as is the variance. So the partial differential equation can be written this way. This is another way of writing it. And here we've got the Greeks, the gamma, the theta, and the delta. But remember, these are all derivatives of the function C with respect to the various parameters. So now, if we assume that the change in S was one standard deviation, remember the formula we got in the earlier module, that the P&L was a multiple of H, and what's in parentheses is, in fact, 0 by the Black-Scholes equation. Black-Scholes assures us that if we can represent the P&L statement as a multiple of this Black-Scholes differential, then it must be 0 because the call price must satisfy this equation. Now remember, this was an approximation of the P&L statement because in order to get this expression, we had to assume that the change in stock prices was approximately S squared delta squared times H. But it's a very good approximation as we saw numerically in the tables.